Hey guys, welcome back to chemistry. So since we've tested over atomic structure, our next unit is going to be on bonding. Today we're going to discuss ions and ionic bonding. Now previously we've discussed what ions are, and in case you have forgotten, let's just brush up your knowledge. So ions, if you want to recall, and I hope you do, are electrically charged atoms or groups of atoms that have been formed by either losing or gaining electrons. And you also were told the reason that they wish to lose or gain electrons was to fill their outer shell. Because now the whole point of bonding is to create a full outer shell of electrons, which will give it the same configuration as a noble gas. When it comes to how you determine if something gains or loses electrons, you can go by a rule of thumb. If it's a metal, the metals are going to wish to lose electrons to another atom and become positively charged ions. So they're going to give away an electron to become stable. Let me do an example for you. If we were looking at sodium, and if you refer to your periodic table, sodium has 11 electrons. So let's draw those briefly. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we need one more electron shell to put the last electron. So what you can see here is that sodium has only one single electron over here in its outermost shell. And it would like, though, to have a full outer shell. So when it becomes an ion, it's going to give away that one single electron. Because when it does that, it now would have a full outer shell of electrons. So this would be our sodium ion, and when it becomes an ion, you put brackets around it, and you put the charge in the upper right-hand corner with the number value first, followed by the charge. So this is 1 plus, and that's because now we still have the 11 protons, but we only have 10 electrons. By giving away that electron, it has a full outer shell, and now it has a noble gas configuration. Now you might ask, why on earth would I want to give away that electron as opposed to taking them? Well, what you wish to do is to do or perform the operation that requires the least amount of energy. So when you're thinking about filling the outer shell, for all of our elements, that would be 8 electrons in the outer shell, except for hydrogen and helium. And that's just because they only have 1 and 2 electrons. So they'd only have the first shell full. But all the other ones, if you recall, like the second shell can hold up to 8 electrons, the third shell 8, and so on. So what you're thinking is, would it be easier for this sodium atom to gain another 7 electrons to fill that outermost shell? Or would it be easier for it to lose just 1 electron to fill that outermost shell? Well, whatever number is the smallest is going to be what it prefers to do because it requires less energy. So that's why instead of gaining 7 electrons, sodium just goes ahead and gives away that 1 single electron. And again, once that happens, we like to put the brackets around our electronic structure and put the charge, which remember, charge is determined by electrons. If you lose electrons, you become positive because there's more protons. If you gain electrons, you become negative because now you have more electrons than protons. All right, now if it's a nonmetal, remember nonmetals are to the right-hand side of the zigzag line on your periodic table. You are going to want to gain electrons from another atom to become negatively charged ions. So let's show an example of that. Chlorine is one that we use very frequently in a whole lot of reactions, so I'm going to use chlorine. So chlorine, if we look at the periodic table, has 17 total electrons. So let's draw those out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Need another shell. 11, 12, 13, 14, 15, 16, and 17. So now if you notice, in my outermost shell, chlorine has 7 electrons, but it would like to have a full outer shell of 8 electrons. So we're going to look, would it be easier for my chlorine to lose 7 electrons so that it would have a full outer shell, or would it be easier for it to gain 1 electron to have a full outer shell? Well, hopefully you're realizing, well, energetically, it would be easier, in other words, require less energy to gain 1 electron than to lose all 7. So that's what would happen. We would come, and now when you gain electrons, you're going to use an X instead of a dot to show that electron that you took from another atom. So it's gained its 1 electron. Now it is now an ion, so it needs brackets around my configuration. And then we need the charge, so 1 minus, because it gained 1 single electron. All right, now that we're up to speed on that, we're going to go into the new stuff, which is determining how will these atoms become ions? Like, where are they going to get these random electrons from, or where are they going to give those electrons to? And that's where this idea of ionic bonding is going to come into play. So when we're talking about ionic bonding, you'll definitely want to know this, is, hang on, let's do this, ionic bonding. So this bonding is going to occur between metals and nonmetals. So remember, metals are those on the left-hand side of your periodic table after that staircase, or rather before, and then my nonmetals are to the right-hand side of that zigzag line. And I know on this video it's got my fingers going different ways, but recognize what I said. To the right-hand side of your staircase are metals, to the left-hand side, I said that wrong. To the left-hand side, you have your metals. To the right-hand side, you have your nonmetals. I'll say that one more time so I don't even get confused. To the left-hand side, we have our metals. To the right-hand side, we have our nonmetals. All right, hopefully we got that clear this time. So this is going to occur between metals, and I'm using a plus sign for and, since you're technically adding them together, and nonmetals. So let's take a look at how this is going to happen. Since ions are going to have charges, they're going to be said to have an electrostatic attraction between the atoms that are wishing to bond. The positive and the negative charges, once they come together, they're held together by strong electrostatic forces of attraction between opposite charges. So you've got to have a positive and you've got to have a negative for this electrostatic, if you're thinking like electricity, an electrostatic attraction between them. Because that electrostatic attraction is there, that's what holds these ionic compounds together. And the thing about ionic compounds, they are super strong. And usually they take the form of salts. Like if you ever, let's think about this, table salt, the stuff you shake on your french fries. The technical formula for that is NaCl, called sodium chloride. Well, if you've ever picked up a piece of salt and you've looked at it, you notice that it's very rigid. It's not easy to crush. It's very hard. And that's typical characteristics of ionic substances. Those ionic bonds are so strong, it holds them together in what we call an ionic lattice. Meaning you have opposite charges, one after the other, alternating in a regular pattern, just over and over and over. So that one piece of salt that you were holding in your hand, it's not just a single compound. Side note, compounds are anytime you've got 2 or more different atoms bonded together, which is what we're talking about. But that piece of salt, back to that, I digress. it's not just that one piece of sodium chloride, it's thousands or millions of little sodium chlorides held together over and over again. So we always get our lowest ratio when we're getting ionic compounds, and we'll talk more about that in just a few minutes. Let's focus on just simply how this bond happens here. All right, so we were saying, how do we know where the electrons come from and where they go when bonding takes place? So I'm going to skip my notes up here a little bit more so you can see this. All right, so look at this little guy right here. This is my chlorine atom. Chlorine, as we very well know from the periodic table, has 17 protons and 18 neutrons. Well, if it is just an atom, which is electronically neutral from the periodic table, that means it would also have 17 electrons, which is what we were looking at in our previous example. So here are all of my electrons that you see, and they're using crosses to indicate them. We've got 2 in our first shell, 1, 2, 3, 4, 5, 6, 7, 8 in our second, then 1, 2, 3, 4, 5, 6, 7 original electrons there. And now that electron right there, and notice they used a dot since they were using crosses for the other ones, that is the electron it wants to gain in order to fill its outermost shell of valence electrons. And again, that's because it's easier for it to gain that one single electron than to lose 7 to achieve that full outer shell of electrons. So before it gained that electron, it was electronically neutral, meaning charge is 0. But once it gains that electron to have its full outer shell, like right here, it gets brackets and it gets charge in the top right-hand corner. And now it has a full outer shell of electrons, and that makes it more stable than it was as an atom because now it has a noble gas configuration. And what I mean by that is it has 8 electrons in its outermost shell, and if you were to add all the electrons together now, this one has 18 electrons. If you look on your periodic table, you'll notice that argon is number 18, atomic number-wise, and it is a noble gas. So this chloride ion has the noble gas configuration of argon. All right, and let's look at what that electronic structure would look like if we wrote it out. So that's what we're talking about, how many electrons are in each shell. So I've got 2 in my, let's go back up here. We've got 2 electrons in my first shell. Then we have 8 electrons in my second shell. And now we have 8 electrons in our third shell. Now, since it is now an ion, we want to show our electronic configuration also that it is an ion. So you put brackets around it as well. And again, we put our charge in the top right-hand corner, so that'd be -1. So that lets anyone who sees your work know that this was not originally the electronic structure, but it is, in fact, the electronic structure of an ion, and they'd be able to tell which one it is based off the number of electrons. What you should also notice, look at these names. Here it said it was a chlorine, I-N-E, atom. But over here, when it became an ion, look at the ending of chlorine. It's no longer I-N-E, it's I-D-E. Anytime that a nonmetal becomes an ion, the change of ending is always I-D-E. So you'd always change for a nonmetal their I-N-E ending to I-D-E. So for example, which was this I-N-E and I-D-E ending. Now you may be asking yourself, well, what if my nonmetal doesn't end in I-N-E? What do I do then? Well, that's actually kind of simple. You just take off the last few letters and again, change it to I-D-E. So for example, if you had sulfur and it lost electrons to become an ion, it would then be sulfide. Or if you had oxygen, you would just change the ending to ox. Odd. So you're just taking off those last few little letters and changing them to IDE. All right. Now let's look at where that electron came from. If we're talking about sodium chloride, which was the example I was using, we have a metal. I'm just putting an M below it so you know it's a metal. Our sodium, and we know that because it's in group number 1. Those are our alkali metals. And then we have our nonmetal, and I'm going to label it NM, chlorine, and it comes from group 7, our halogens, so it is a nonmetal. And remember, you always have to have a metal bonded to a nonmetal for it to be ionic bonding. So we were looking at sodium previously too, and we saw that sodium had 11 electrons. So let's sketch those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then here, that makes 11. So we had spoken about how that 1 electron would be lost so that sodium would have a full outer shell of electrons, but we didn't say where that electron would go. Well, that's why we would have a nonmetal such as chlorine so that it could bond with it. So originally, chlorine had 17 electrons. And now notice I'm using crosses for my chlorine. Whenever you're indicating bonds, you're going to show bonding. One atom needs to be dots for electrons, and the other one needs to be crosses. It doesn't matter which you choose, whether you put your metal with dots or your non-metal with dots, or vice versa. Crosses for your metal, crosses for your non-metal. As long as you use 2 different ones, a dot for one and a cross for the other one. And these are called dot and cross diagrams, is what Cambridge refers to them as. All right, let's get the rest of our electrons here. 4, 5, 6, 7, 8, 9, 10. Then we need 7 out here. 1, 2, 3, 4, 5, 6, 7. All right. And to make this easier so you can see better, I'm going to put that electron on my right-hand side just so that you can see where this bonding takes place. All right, so when chlorine becomes a chloride ion, we discussed that it would want to gain 1 electron to have a full outer shell. So that's why you have a metal with a nonmetal when you're doing ionic bonding, because that electron that sodium wanted to lose, well, it can't just go out into space. Something has to take it. And that's where my chlorine comes into play. Sodium gives that 1 electron that it didn't want to my chlorine. So now, once that electron has been given, I get my sodium ion, and notice it has the 1 plus charge because it gave away its 1 electron. And now I have my chloride ion. Remember, nonmetals change their ending to IDE when they become an ion. So it's a chloride ion instead of chlorine. And here's the dot to represent the electron that it took from sodium. And now it has a 1 minus charge because it gained 1 single electron. So the way this naming thing works is the metals don't change their ending whatsoever, ever. So sodium is still just sodium with the word ion on it. When they come together to make my compound, I just put those 2 names together, sodium, and then I use chloride. So the name of your metal stays the same, but then your nonmetals ending changes to IDE. So that is sodium chloride. All right. Cambridge specifically wants for us to look at the formation of ionic bonds between groups 1 and 7. So that's one thing that we just done. We were looking at sodium chloride, NaCl, and notice those are written side by side with no space between them once they become that compound. And you'll see here's where my sodium donated that electron. And right here is where my chlorine took that electron to become chloride. And again, once that happens, here's my full shell of electrons for sodium. And now my chloride ion has a full outer shell of electrons. And remember, the attraction that holds those two together is called the electrostatic force. And remember, electrostatic force is the attraction between oppositely charged ions. You have to know that. Hey everyone! All right, so I had a little hiccup in between the last example and this example and had to start a new video because we had an announcement. But I'm back, and let's look at another example because what we're doing now, you're going to be responsible for on your own momentarily. So I want you to have something else to look back on that will make it easier for you. So the first thing I want you to notice is on my notes, we're looking at magnesium oxide. All right, so that's made up of magnesium metal and oxygen as my nonmetal. So I'm just going to label those metal and nonmetal, so you do understand that with ionic bonding, you do have to have a metal and a nonmetal. Now, what you see in my notes right now is that the final product where you have just your ions formed without electrostatic attraction holding them together. But what you're also going to have to be able to do is to show how those electrons move from the magnesium to your oxygen to form your magnesium ion and your oxide ion. And notice they made a uh-oh right there. That is not an oxygen ion. Remember, we have to change the ending to IDE. So that's an oxide ion. So that is not right. I should have checked their notes. All right. So I'm just going to jump down here and show you what you would need to do to show how this ionic bond formed. All right. So here's my magnesium. And what I'm going to do is show only the outer shell of electrons. And I know the number of outer shell electrons based off the group number. So magnesium has 2 outer shell electrons. Now, I know every time we have drawn atoms before, we've drawn each and every shell, which is completely correct. But when it comes to bonding, to keep things neater, we're allowed to just draw the valence shell of electrons, so just the outer shell. And that's because with bonding, they're the only ones that are involved. They're the only ones that can be moved or the only ones that can receive electrons. So with bonding, we can show just the valence shell, the outer shell of electrons. And again, you know how many that is based off the group number. All right, then I'm going to come over here to oxygen. Oxygen is in group number 6, so that means we have 6 valence electrons. So here we go, 1, 2, 3, 4, 5, 6. All right, so remember the goal of bonding is to fill the outer shell of electrons so we have a full shell of 8 electrons, so we have noble gas configuration. And with metals, recall, we want to give away electrons. Whereas with our nonmetals, they're going to want to take electrons to fill their outer shell because that is more energetically favorable, meaning it's easier for them to gain a couple than to lose a whole bunch. So let's look at magnesium here. It's got 2 outer shell electrons. So it's going to be easier for it to give those 2 electrons away than it would be for it to take in a whole 6 more to fill it. So we're going to show how that happens. So here's magnesium. If you notice, oxygen needs 2 more electrons to have a full outer shell. And it's going to get those electrons from magnesium. So magnesium's going to give 1 electron there and 1 electron there. So now, notice I have an arrow going because that shows a reaction took place. Now I can have magnesium, and since it gave away that outer shell, now its innermost shell is actually full because the innermost shell of magnesium has a full 8 electrons once we get rid of that outer shell. But remember, when they give away electrons, they become an ion, so we need brackets around my diagram, and then we have to have the charge in the upper right-hand corner. So magnesium gave away 2 electrons, so it has a 2+ charge. Now my oxygen, we're going to show the original electrons it had with the X's, just like it was on the previous one. But where we gave those electrons to oxygen from magnesium to create my oxide ion, we draw them as dots because that's how we represented the electrons on magnesium. And then, of course, we're going to add our brackets because now oxygen is no longer an oxygen atom, but it is now an oxide ion. It's got 2 more electrons, so it'll have a 2 negative charge in that upper right-hand corner. And below here, I've written it out for you in case you missed any of what I said. So now we have magnesium oxide. It's an ionically bonded compound. And just to recall, remember, compounds have completely different characteristics than the atoms they began as. Because remember, magnesium was a metal before, and oxygen was a nonmetal, but when they come together, they create a hard ionic substance. Because remember, ionic compounds are hard. They're very hard. And that leads us to what they look like. I've been describing the construction of ionic compounds as giant ionic lattices. So that's the structure of an ionic compound. And this lattice, what it's referring to is that arrangement of atoms that creates up the 3-dimensional space. So like before when we talked about sodium chloride, the table salt, being that hard little piece of salt that you can pick up, well, every ionic compound is similar to that. It may be a different color, but it still has that hard crystal structure. And so remember, each little crystal you see is not just a single, like magnesium oxide, or just a single piece of sodium chloride. It's hundreds or thousands of those sodium chlorides, or like our last example, the magnesium chlorides, just over and over again. But remember, they have to alternate charges. So they're arranged in a very ordered pattern in a repeating fashion. So that's why we call it a lattice. That lattice consists of the regular arrangement of alternating positive and negative ions. So we have a little structure below here that you can look at for reference. So you'll notice my chloride ions here are larger with the negative charge because it has more electron shells than sodium with its little positive charge. And sodium's got fewer electron shells after it becomes an ion, so it's smaller than my chloride ion. But you'll notice for every negative chloride, I have a positive sodium. Then a negative chloride, positive sodium ion, negative chloride, positive sodium, and so on. And notice that doesn't stop in 2 dimensions. That goes all the way through the structure in 3 dimensions. Now, it's always in a regular pattern, but it keeps on repeating over and over in every direction. So, for instance, like this little positive sodium there, well, it's connected to this negative chloride ion in the back and this negative chloride ion in the front, along with this negative chloride ion to the other side of it. So that just repeats over and over in every direction, but it is always alternating positive and negative charges, and it's always in that regular structured arrangement. All right, that is it on your notes. Now we'll work on getting you to do some practice. Bye, guys.